We have seen that the first issue in congestion control is that it's not a good idea from the stability viewpoint of the network to allow all sources to send as much as they can. We need to control the rates such that the network doesn't go into problems like congestion collapse or more mildly, very wild inefficiencies. How to control the rate is the next topic. What should be the control objective? We have seen that maximizing the total rate achieved by a network is not a good idea. We need to have a criterion that considers fairness. The first proposed criterion for fairness is called max-mean fairness. It's implemented in a number of systems, and this is where we stopped last time. We have seen that intuitively the definition of max-mean fairness is that it tries to give the same to everyone, and then if it's possible to give more than the minimum to everyone, you give it, trying not to give it at the expense of those who have a small rate. Formally, it has been defined with a definition that's a bit more complicated, that will not reply, and there is an existence, a unicity theorem that says that for all the network models we have, there is one unique max-mean fairness allocation, and even better, there is a practical algorithm for determining it, at least a centralized algorithm here, that says in a given network, if you wonder what should the max-mean fair source rates for all sources, you do the following. You start giving the same to everyone until you hit some capacity limit. Those sources that hit the capacity limit are called frozen. And then you continue increasing the rate of all sources that are not frozen until a new link becomes a bottleneck, is saturated. And you do that step by step. If your network is finite, at every step you saturate one link or one source if sources are unable to follow the links. And so the algorithm will converge, and it will converge to one allocation that is always the same, is the max-mean fair allocation. We don't do the proof of that theorem. Instead, we will see how it works on this example. This is the same example we've seen before with two links, three types of sources. So the algorithm says at step one, you allocate the same rate to all sources. So this is a small optimization problem. Find the max value of t. We want to increase as much as possible. That means we're maximizing the rate. I call it t, this rate. Maximize t. That is the same to all, and that satisfies all the constraints. So the constraints are that if I look at the first link, t plus t, 2t must be less than 10, and the second link, t plus 9t must be less than 10. So the max of the constraint is that t is less than 1. The solution we can increase up to t equal 1. So in the first step, we give 1 megabit per second to all the sources. This is what we did in the pure egalitarian case. What are the sources that are frozen at the end of this step? Those are the sources that use a link that is saturated. When I give t equal 1 to everyone, the traffic on the first link is 2. This link is not saturated. The traffic on the second link is 10. That link is saturated. The sources that are frozen are all the red and green. So the red and green are frozen. I don't touch them. Their allocation will not move anymore. So I do the second step. Now, I need to continue increasing the rate of the sources that are not frozen. Here there's only one source that is not frozen, the blue. So I need to give the max possible to the blue while not touching the rest. That gives 9. Then the blue is frozen as well. Everything is frozen. The algorithm has converged. And we have converged to this allocation, which we knew already is the max-mean fair allocation. This is how the algorithm works. It's your turn to try it. Here is another type of network. It has 4 links, 5 sources. Every link is of capacity C. What is the max-mean fair allocation in this network? I close the poll in a few seconds. Fantastic. Dirac on the first solution, which is correct. Here it's a very simple case. You increase the rates of everybody and you reached the limit everywhere on all links. It's a very unlikely network, but that serves two purposes. First, to check your understanding of the algorithm. And second, to illustrate what max-min fairness gives. Max-min fairness, which again is used in some environments, has been criticized by looking at scenarios like this one. In this scenario, you have sources like the blue that use a very small fraction of the resources of the network. The red source uses many, many more resources. Max-min fairness will give the same to both. Is it fair? Is it not fair? We don't know. We're trying to find axiomatic definition of fairness. But some people have said this definition of fairness is too strict. I mean, if you're using a local link or if you're using a link that crosses the entire globe, the entire Earth, should you be given the same rate if it is possible by the laws of max-min fairness? Some people say no. If you use a lot, it's fair to give you less because the red uses 4 links, whereas the blue uses only 1. So some people think that X0 should receive less than the blue. Is there a way to make sense of this intuition? There is, yes, and it is what is perhaps the most well-accepted notion of fairness, which is called proportional fairness. So proportional fairness has been invented to go beyond max-min fairness and to address this attempt to reconcile two viewpoints who want to be maximally efficient while being fair. And it uses the following criterion. It's as complicated to define as max-min fairness, so I'm sorry for that. So the context is the same. I have rate allocations that are possible, that if you're an oracle and you have the complete view of the network, you have the constraints. So rates are feasible or not feasible. Among the feasible rates, we say that an allocation of rates, X, is proportionally fair if any move away from X would have a relative balance computed in that sense, which is negative. What is the relative balance of the move? Well, it's the sum of the delta, of the relative delta of all the rates. If you move, that is, if you have Y instead of X, every source, say source S, will have a delta, which is YS minus XS. The relative delta is YS minus XS divided by XS. So that is how much source S has, more or less, in relative terms. If I get a new allocation, some sources will have 10% more, some other sources will have 10% less. And I say that a move is a good move in the sense of proportional fairness if this balance is positive. If, in contrast, I have found a point where any move has a negative balance, that means this point X cannot be improved. It's a stationary point, and I call it proportionally fair. Whether that exists, whether it's unique, that's another story, but let's take that as a definition. So in other words, an allocation is proportionally fair if for any other allocation, if you try to deviate from the allocation, if you do the balance of what you obtain after this deviation, in average, it's negative. So you can give more to some, less to others, and if you're a social optimizer, you would like that the total sum of all those deltas, relative deltas, is negative from any other allocation. That means you cannot improve your allocation from the viewpoint of fairness. Now, if we compare to max-min fairness, we see a first distinction. The first distinction is that what matters is not whether you can increase. The definition is very close to max-min fairness, but has some differences. The first definition is in max-min fairness, what mattered was whether you can increase someone that was at the expense of somebody that was less better off. So what mattered were the absolute values of the rates that are allocated. Here it's the relative values, which makes sense in some sense. If you're trying to access the internet over a GSM link and you painfully get perhaps 10 or 15 kilobit per second, if you move from 15 kilobit per second to 30 kilobit per second, that's a fantastic increase for you. Now, if you access from home over a fiber network at 2 megabit per second, whether you get 2 megabit plus or minus 10 kilobit per second, you don't care. So it has no importance for you. Max-min fairness will treat those 10 kilobit per second equally important for the two cases. Here we say no, it's relative things that should matter. So that's the first difference. The second difference is in the criterion we take the sum. So we integrate all the effects, so which will have a global effect. Whereas in max-min fairness, we look the impact on every individual rates, but do not weight the impacts. We just take every individual increase and we look at it individually. This second attempt is dictated, this second effect is dictated by the desire to apportion the rates to the resources that you use. If you use many, many resources, by decreasing a bit your rate, the global effect might be large if taking away a little from you allows to give a lot to many others. So that will be accounted for by this. That's the intuition. So let's test our intuition on this example. Here are two proposed allocations, A and B, for two network scenarios. Which one are proportionally fair, if any? You recognize the allocations we've seen already in the previous questions. Try to use your intuition more than the formal method, because we will see the formal method in more detail soon. Five more seconds and I close the poll. Interesting. So B has a lot of attraction. Many believe that B is max-min fair, but many believe that none of them is max-min fair. If we look at A, the A allocation, then we see that it gives the same to the large flow, to the long flow and the small one. So based on the story I said before, intuitively it should not be proportionally fair. So A should not be proportionally fair. Now if we look at B, we see that B gives 1 megabit per second to this flow and 1 megabit per second to each of those. Now this flow is using more resources, so they get the same here. Where is the bottleneck in this network? Well, we see that here there's lots of freedom. This link is largely underutilized unless we give a very, very large amount to X1. So the bottleneck is really this one here. So this is a network where here is the bottleneck, and we give the same to the red and the green. Probably this is not what proportionally fair allocation would like to do. But let's check. Let's just do the maths. So, oops, sorry. We can check formally for the first one. We have an allocation x, which is given here. Can we do a move that has a balance which is positive? And the answer is yes. I can increase, x0 is our victim. This is our target, the red flow. We think it receives too much. So let's try it. If we give less to the red flow, we do x0 becomes x0 minus delta. Of course, if we reduce the red flow, we can increase the blue. So we can do xi equal xi plus delta. And of course, we have to do it such that it's feasible. So delta should be less than c over 2. So any delta that satisfies that is another feasible allocation. What's the balance for this? Well, for one flow, the red I have done minus delta divided by the quantity it received before. For the 4 other flows, I've done plus 4 delta over the same denominator. The balance is positive. So that move is better. You should move in that direction. That new allocation is better than the one before. So the one before is not proportionally fair. Still don't know with this theory whether there is a proportionally fair and how to find it, but we know this one is not proportionally fair. We can do the same thing here for the second example. I can increase x2, which is the green, by some little amount, delta, and decrease x0. X0 is the red flow. Here I'm assuming I give the same to all similar sources, which is true in general, but I don't prove. But if I increase by 1 delta each of the green, I need to decrease the red by 9 delta. Okay. And if delta is not too large, then this new allocation is feasible. Now, if I do this, because I have decreased the red, I can also increase the blue, because the red is now freeing some capacity on the first link. This is a move I can do, while of course trying to utilize the network as much as possible. If I do this move, we see that the total rate of change is positive. Therefore, we should move in that direction. This allocation is not proportionally fair. This is the formal proof. Now, why do we do those formal proof for those examples? Well, because it gives us an intuition for the formal result we know about proportional fairness, which is given here. Proportional fairness is in fact the same as maximizing the sum of the log of the rates subject to the rates being feasible. In other words, if you want to compute the proportionally fair allocation, you solve a convex optimization problem, which is given here. Now, since the set of feasible rates is defined by a polytope, it is convex. Since the log function is strictly concave, there is a unique maximum. So there is a unique proportionally fair allocation. So lax max mean fairness, at least for simple network models, proportionally fair also leads to a unique and existing solution in any network, which of course is required, otherwise we would not do that theory. Why the log? Well, an easy interpretation is to say this story of moves, we can interpret it as an optimization algorithm. If I want to find the max of this, and I do a randomized algorithm, I want to maximize the sum of the log, or in general, if I want to maximize a function j of x in a given space, then I can start from a randomized algorithm consisting starting from x, then do a move in a direction that increases the x. Right? And if you do this, you will move until you reach a point that, roughly speaking, you cannot increase anymore in any direction around you. The j is decreasing. If you reach this point, you've reached the maximum. Now, what is the gradient of j? Well, it is sum of dx over x, which is the infinitesimal approximation of the delta x over x. So when you have reached the proportionally fair allocation, any move that you do around, at least locally, as a first order approximation, should have a balance computed like this, which is negative. There's a bit more to show the proof, but that's the intuition. Another way to think of it is if what matters are the relative increases, it means that what you really are maximizing is the log of your thing. If you, because the derivative of the log will be, will give this formula dx over x. So that's a general statement we have in any optimization system. Let's go back to this example. We have seen that the max-min fair allocation for this network was not proportionally fair. So what is now the proportionally fair allocation? Well, the theory says I need to maximize U subject to the constraint. U is the sum of the log of the rates. There are 5 rates here, subject to being feasible. Now the feasibles here are 4 constraints. So you recognize convex programming. Convex programming is about minimizing concave functions over convex sets. So this is a convex set, and the log is concave here. And how do you solve convex programming? Well, you use MATLAB or some other package. Here we are in one of the very academic cases where we can do it manually, so let's do it. First, we can see that if we analyze those inequalities, there should be equality everywhere, because those inequalities are related only by x0 and x1. For every inequality, there is one variable that appears only in this inequality. So for example, if I have a solution, a feasible point, where there is not equality here, so the inequality is strict, then I should increase x1 to reach equality. I should because I can. Increasing x1 doesn't change anything in the other constraints because x1 does not appear in the other constraints, and will increase the objective function which contains the log of x1. So any feasible point where there is not equality in all of those 4 cannot be the optimum. Of course, this rarely happens in convex programming. I mean, the difficulty in convex programming is knowing what inequalities are binding or are not strict, and when inequalities are known with equality. In general, if you want to determine this, you have exponential complexity in determining this. But in this tailor-made example, we are in this happy case. Therefore, there must be equality everywhere, which means we can reparameterize our problem with a problem that depends only on one variable, x0. So we must have x1 equal x2 equal c minus some x, where x is the thing we want to optimize for. And how do we do this? Well, we have to, the utility is now a function of this optimal x, which is log x, this is x0, plus each of the blue sources has a rate c minus x, so we have 4 log x. So now we have to maximize something that is much easier to do. It's still a concave function, but of one variable, so we compute the derivative, and when the derivative is 0, and if the point where the derivative is 0 is within the interval where those things are possible, then it must be the maximum, which is the case here. We obtain x star equals c over 5. So, end of the mathematical parenthesis. The proportionally fair allocation gives 1 over 5 to the blue, to the red, and 4 over 5 to each of the blue. In fact, accounting for the fact that, at least in this naive case, where the red uses 4 times more resources than the blue. So, in some sense, it needs to pay 4 times. So, in money, if we allocate 1 franc for the use of each of the resources, x0 and all the sources will pay the same thing. This is what the proportionally fair allocation will do and how we can compute it for this example. Test your understanding on this. We have seen that the max-min fair allocation was not the proportionally fair allocation. What is the proportionally fair allocation for this example? close the poll in a few seconds. And the majority vote is for number 4, which is correct. We can do it in different ways, but we can first eliminate the things that are impossible. The first allocation we know is not proportionally fair. We've discussed that already. Now number 2. Number 2 is not fully exploiting, so x0 has increased x2, so the green, and has therefore increased has increased the green, decreased x0, but the blue is not receiving any improvement from there. This is so this is certainly not the proportionally fair allocation, because I can increase the blue in this allocation without touching anybody else. So the balance is positive. I can do a move that is positive. It's not proportionally fair. Such an allocation is said to be non-Pareto efficient. Pareto efficient is another term that we will not see in detail, but is sometimes used. That means an allocation is Pareto efficient if you cannot increase it unilaterally. So something like this second allocation, you can increase it unilaterally. You can increase one rate without changing anything else. So if you can, you should do it. So all the fair allocation, max, mean, proportionally fair, are Pareto efficient when we have tried to give the max to everyone, and when we want to change that, if we want to give more to some, we're obliged to give less to others. So we're discussing Pareto efficient allocations here. Now 3, the allocation 3 is Pareto efficient, but it goes in the wrong direction. It gives more to the red than the max mean fair allocation. So it's not approved, but intuitively it's going in the wrong direction. It would be surprising if it's the proportionally fair allocation. Since this quiz says there's only 4 possible answers, it must be the number 4. Admittedly, that is sufficient to work in a test, but we would like to understand why. Then we can do the maths. It's as before, there must be equality in the constraints, because here the blue and the green are independent. Therefore, there must be something like this at the optimal. So we need to find an x, the x star, that maximizes the log of x0 plus the log of x1 plus 9 log of x2, which gives this, and then it's a high school exercise to find the max. You take the derivative. You find that the derivative is for x equals 10 over 11. So it will penalize the red source by giving it a little bit less than the max mean fair allocation. Voilà, that's the theory of proportionally fair and max mean fair allocation. Now, if there are 2 theories of fairness, there's a problem. I mean, we would like to have one unique theory. Right? Many people believe proportional fairness is the best one, but as we'll see, TCP does not do exactly proportional fairness. So people have used a more general concept, which is called utility fairness, which we have seen already. In fact, when we say that proportional fairness corresponds to maximizing the sum of the log of the rates, it means we assign to a source a utility, which is not its rate, but the log of the rate. So the social optimizer that implements proportional fairness should not maximize the sum of its rates, like in the naive optimizer we saw last week, but the sum of the log of the rates. Now, why the log? Well, we've seen axiomatic definitions, because we care about relative values. Some people have proposed to use more abstract functions. So in general, if you assign to a source I a utility ui that depends on its rate, according to some probably concave and increasing function, like log, but not necessarily like log, then you obtain what is called utility fairness. So an allocation is utility fare according to some utility function if it maximizes the sum of the utilities. And if the utilities are all concave, then there is a strictly concave, there is a unique such allocation, like for proportional fairness. That's the first thing. The second thing to observe, it's results by Walrand and Moe, that shows that we can approximate. So first thing is max-mean fairness is not a utility fairness. So max-mean fairness does not integrate things. It looks at individual changes. So there is a result that says we cannot cast max-mean fairness as a utility fairness. However, it is a limit of utility fairness. So in practical terms, we can approximate it by a utility fairness where the utility function is something like this, something concave, but which has something that is close to a step function. Or more exactly, if you take a family of utility functions, like the red one, for example, this type of functions, 1 over 1 minus x over m, when m gets large, in the limit, what you obtain is a step at 0 and minus infinity at 0 here. So if m is large but not infinite, you have something that looks like this. Assume for every m, you compute the utility, the allocation that this utility fairness gives you, then the limit of this allocation, when m goes to infinity, is exactly the max-mean fair allocation. But it is not, of course, the utility function itself, u sub m here, does not have a limit when m goes to infinity. It's 1. And if the utility is 1, then maximizing 1, any allocation is 1. So the limit of the utility of the allocation is not the allocation of the limit of the utility function. It's one of those interesting cases where limits cannot be interchanged here. But for us, it means we can reason about max-mean fairness as being something a bit like proportional fairness in the sense that it has a utility function that is a bit less friendly, less smooth than proportional fairness. So at this stage, what did we see? We saw that sources should adapt their rate and to the state of the network. We should do congestion control in a network. And in order to do congestion control, we should try to implement some kind of fairness, which can be ideally proportional fairness, but max-mean fairness is an option. Questions so far? No, then let's continue. The next step is, of course, how do we implement a form of fairness in a network? If you have a small network, you could imagine an SDN controller that computes the rates of all sources and dictates the rates. And it can be done. It's done in some industrial environments where you can control the rates by a central controller if the sources are well defined and well behaved. For example, PMU streaming, industrial devices that are always controlled and perform the same function always. Now, if you have a more dynamic environment, not to speak of the internet, which is the worst in terms of dynamism, then you cannot imagine that. You cannot have a global controller that will do what we did on the board here, compute the rates, allocate them to the sources. That will not be feasible. So we need to have practical and hopefully distributed algorithms for doing that. Everything that is possible has been done and is found in the internet. You find in particular algorithms for computing the rates according to some form of proportional fairness. So most notably in CDMA networks, you allocate the rates to sources according to proportional fairness. Now, what are the rates? Those are the modulation rate, the channel rate between a source and a base station. So here the goal is to share not the entire internet, but the local air, the radio waves. And this is done by allocating proportional fairness. Of course, here it's possible to have a local controller in a base station that will dictate the rates to all the mobiles that are connected to this base station. There are other networks, industrial networks like MPLS networks, that try to allocate statistically rates to big users. They also tend to do it using proportional fairness most of the time, and using a practical method which is called rate base. Rate base means you have a means to speak to a source or to a collection of sources if you're interconnecting enterprise networks, for example, and where you can put a rate control. You can say to that source, send at 2 megabit per second, not more. You can do that in a mobile device. You can do that also in computers, as we will see in Lab 5, using traffic control functions. Now there are, but that is, I would say, the easy and intellectually easy, technically very difficult to do, because it works only in local environments or in environments where you have complete control on what happens. In other environments, people have tried other methods that are more distributed. In gigabit LAN and multi-gigabit LAN switches, there is what is called a hop-by-hop protocol, where a node, when it starts to feel congested, will send back pressure signal downwards to the other nodes that are downstream, that are upstream, to inform them to reduce their rate. This form of congestion control is called hop-by-hop. And then an interesting research exercise is, for a given hop-by-hop back pressure algorithm, what kind of fairness is that implementing? There has been studies on that, and essentially they are not fair in any kind, but they are used widely in local environments where what matters is not really fairness, but avoiding congestion collapse. That's all. But more interestingly and more widespread is what is done in the internet. In the internet, we use what is called end-to-end or edge-to-edge solutions, where nobody is in fact computing the rates, nobody is solving this optimization problem that we have seen, but there is a distributed algorithm in every source, in each of your computers and mobile device, which is implemented in TCP, where we have an adaptive algorithm that increases or decreases the rate such that, in average, it will approximate something close to proportional fairness. This is what we will see next. And this distributed algorithm is based in the internet on a very simple control law, which is called additive increase, multiplicative decrease, that we will see now. It's the basis of congestion control in the internet at the layer of TCP, so for fundamental congestion control, and it has been reused in any other situations because of its simplicity. I will now explain how it was developed. So we will go back through the original paper that explained that. Additive increase, multiplicative decreased was originally developed by Raj Jain for the DECnet network. That was a network pre-TCP-IP that was running on digital equipment, VAX, and that kind of machines. For those of you who've heard your parents talk about computers of the 80s and the 70s. And then, when there was this congestion collapse that I mentioned in the internet, because TCP did not, or no other place in TCP/IP implemented congestion control, it was copied and reused in the internet. And the idea is based on a very simplistic model, and the beauty of it is that this simplistic model that was later analyzed in a global setting proved to do something close to proportional fairness. So this very simplistic model is the following. As usual in computer science, if you want to do something that works, you have to make it very simple. So this very simple thing here is, think of your network as a single link that has a given capacity C. Real networks are more complicated. There are multiple bottlenecks, but think of it as a single bottleneck here. You have a number of sources. Each of them has a rate. So xi of t is the rate of a source. And you would like to allocate to the sources the rates that are fair in some sense. Raj Jain did not talk of fairness at that time, but of an explicit form of fairness, but he wanted to avoid congestion and have something that is, roughly speaking, fair, as we will see. And the idea to make it distributed is to test the water. So the sources send, then they see what happens to their traffic. They sense whether the network is congested. I mean, how can you sense whether a network is congested? we will see in a second. But one way to sense that the network is congested is to require, for example, all the routers and perhaps the switches on the path to mark in the packet header how busy they were. You send a packet that goes through a buffer somewhere. If that buffer is close to congested, which is known to the local machine, you can flip a bit in the packet header. And if you're using TCP or any protocol that has feedback to the source, you can, at the destination, echo what you have seen in this place in the packet header and send the information back to the source. This is what is called ECN in the internet. We'll see that the internet uses a slightly different mechanism. But in DECnet, this was exactly what is called. So in the DECnet architecture, in the IP of DECnet, the layer 3 of DECnet, there is one bit in the packet header, which is called the DEC bit. It was so wonderful and powerful that it has received the name. So when a destination receives a packet with a DEC bit marked to 1, it sends in the acknowledgement back to the source, it sends a feedback, and this feedback is 1 if it is congested and 0 otherwise. Now, to analyze this mathematically, I make a very simple model where I assume that I have a network that has a capacity C, and this feedback is simply dictated by whether we are exceeding the capacity or not. In this simple model, if we exceed the capacity, everybody exceeds it, so everybody will receive the same feedback. Well, we do a break, and we will discover after the break how this works. So here is our model. We have a number of sources. Each of them receives a feedback, and when it receives a feedback, it should, of course, reduce the rate when the feedback is congestion, otherwise increase it. That's the principle. You test the water, you try to send as much as you want. When nobody says to you, don't, then you continue increasing until somebody says, stop, that's too much, then you decrease. That's the idea of this distributed control. What form should the increase and decrease take? Well, in this model, we use very simple formulas. Simplicity is linear, usually, in some scale. So that gives those formulas. If the feedback is 1, that means there is congestion, then you apply a linear transformation to the sources. All sources apply the same transformation with the same parameters, but the resulting rate, the new rate, xi of t plus 1, depends on the previous rate. So if I use those here, we can give names to those terms. The term U1 is the multiplicative decrease factor. So if I receive a congestion signal, I want to decrease the rate. So I multiply the rate by U1, and I add V1. So U1 should be less than or equal to 1, and V1 should be less than or equal to 0. We want to decrease. And conversely, when we receive no feedback or positive feedback, or feedback that there's no congestion, we want to increase, which means we should have this. Those are the constraints we have. To understand how it works, here is a small simulation of 3 sources that are sharing one bottleneck with the given parameters. So when there is congestion, we decrease the rate by a factor of 0.5, U1 equals 0.5. When there is no congestion, we multiply the rate by 1, which means we don't change it for the multiplicative factor, plus we add 1. So this is a simple multiplicative decrease. We divide by 50% when we have negative feedback, and we add 1 when there is positive feedback. I have 3 sources that are running this on a given network, and sources 1 and 2 start at the same time, and sources 3 starts at time 100. Then we see what happens to the total rate here. The total rate nominally is 10, so we can exceed it with this algorithm once in a while. And then we see that this algorithm doesn't converge. It has oscillations, but in average, it tends to oscillate around something that is perhaps good in the sense that it's maximally efficient. It's close to 10. Of course, if the true capacity is 10, you have a problem because you reach 12. But if you have a safety margin, you say the declared capacity is 10, but it means the true capacity is perhaps 12 or 15. Then this scheme will work. We'll see also that what happens, we had source 1 that starts from a small value, source 2 starts from a large value. We see that very quickly they converge both to the same value. So it is, this algorithm has some kind of fairness in it. And we see also that they adapt very quickly to the eruption of source 3 that starts here. Whenever it starts, it forces everybody to decrease. And those 3 sources have more or less the same rate when the 3 are present, which means we have achieved some form of fairness. We have shared the capacity of this link by giving 1/3 to each, and we use the link practically at its maximal capacity. So we have implemented a distributed algorithm that is approximately, in average, over time, is trying to perform a rate allocation that seems to make sense here. Question?
Yeah. Why does it oscillate even for a stable system?
Well, because it's in the nature of the algorithm. You receive, you're always increasing or decreasing. And as long as nobody tells you that's enough, you continue increasing until somebody says that's enough, and then you decrease. Then everybody will decrease, and then you can increase again because by everybody decrease. So if you wanted something that converges to a stable equilibrium, which exists, it's the topic of randomized algorithm, you would need that the gain of this algorithm decreases itself. So when you increase, you don't increase by a constant amount, and you would need to adapt this in typically 1/n. But that is not so much applicable to something like the internet, the kind of algorithms you would use to something where you want to reach a stationary regime for an environment that is stable. But in the internet, of course, the sources come and go. So you never reach a truly stable regime, at least in that sense. Okay, that was so far only an illustration of what this algorithm means, that kind of scheme means. Now we want to do an analysis to see what are the good values that we should give to the parameters here. So remember those parameters, we have a factor that is the multiplicative decrease factor. That's the one we apply when we decrease because we have perceived congestion. An additive decrease term. We have a multiplicative increase factor and an additive increase term. We can visualize the algorithm, at least for the simple case of 2 sources in this space diagram. I'm plotting on the x1 axis the rate of a first source, on the x2 axis the rate of a second source. I'm assuming a simplistic network scenario where there are only 2 sources sharing a bottleneck of capacity 1. Then the constraints are that x1 plus x2 are less than 1. So when I am on this line, that means I am using the capacity of the bottleneck at 100%. So the algorithm should bring me around that line. But there is another line which is shown here. That's the line where x1 is equal to x2, which is the line of fairness, at least for this very simple scenario. Now you could ask, is it max-min fairness or proportional fairness? In this simple network, where there is only one resource of capacity C, max-min fairness will give C over n to everyone. And so will proportional fairness. So if there is a single link to share, the issue of fairness is fairly simple. You give the same to everyone. Of course, this is assuming lots of things in this model. In reality, there is never a single link. For example, if a source has a limit, the source cannot send more than something, then we can model this by putting a link to this source that has a capacity which is different for every source. So this model doesn't pretend to be a true model of the network, but within this model, if we reason about fairness, this is what it gives. So if we want to be fair, we should be on this line. And if we want to implement some form of fairness that is also Pareto efficient, we should be around the red corner there. This is where the algorithm should bring us. Right. And it brings us by doing increases when we are below capacity. And here, when we reach capacity or exceed it, then we'll receive congestion feedback that will force a decrease here. Now, does any set of parameters provide something that will lead us towards this red corner? That's the question. Before answering the question, let's try to map those concepts, additive, multiplicative, to the geometry of this example. Here, I'm proposing two possible moves, so two possible increases. I am at an allocation x. I receive some positive feedback, so no congestion, y equals 0. I can do additive increase. Additive increase means the u parameter is equal to 1 and the v parameter is positive. Multiplicative decrease means the v parameter is 0 and the u is larger than 1. Which, if any, of the two moves A and B correspond to additive increase and multiplicative decrease, and multiplicative increase? I close in 5 seconds. And the majority is right. A is additive increase, because if we add to x1 and to x2 the same amount, then we add a vector that's proportional to the line x1 equal x2. B is multiplicative increase. This is multiplying all the coordinates by the same number here. That seems completely trivial, but if you've understood that, then you've understood everything about additive increase and multiplicative decrease. Because now if we put things together, we should think of this algorithm as something that will move randomly depending on the state of the network, according to doing moves that can be any of those 4 moves or combinations of them. But the goal is to get to the red corner there. So if we start from some initial condition is, for example, sources 1 and 2 were using the bottleneck, and sources 3 starts. So it's like with distance vector routing, the initial conditions are usually very far away from the optimal point you want to reach. Now, by moving, if you want to get closer to the red, what should you do? Well, first you see that if you want to get closer to the, well, the first thing you see is that when you increase, you will get closer to the boundary. But if you increase, but are you getting closer to the diagonal here? Is the fairness improving? Now what we can see is that the only way to increase fairness, the only thing that increases fairness here out of those 4 moves is the blue one. If I do a green move, I increase the rates of everyone, but the unfairness remains the same. One source had less than the other. After the move, the proportions are the same. So the fairness has not improved with the green. Same with the yellow. And with the red, it's even worse. If I do additive decrease, I make things worse. I make the things more unfair than it was at the beginning. Fairness is measured by how far, what is the angle from this line here. Or if you want, the ratio x1 over x2 here. So we see that in this context of linear controls, the only place where you have an opportunity to increase fairness is when you increase, and if you increase additively. So you should do additive increase, and you should put all your eggs into the basket of additive increase. In other words, you should not do, you can do multiplicative increase plus additive increase, but when you do that, you will use some of your increase without making fairness better. And since the only moves that improve fairness are the increase ones, you want to put maximum things for fairness here. So you should do additive increase. And what you should certainly never do is additive decrease. So you should do multiplicative decrease. You should do additive increase, and probably as little multiplicative increase as you can. In other words, if you have such a control, the only thing that makes sense is to do additive increase and multiplicative decrease. If you do any other combinations of those, you will have something that will not converge or not converge very fast towards a fair allocation. In particular, if you do multiplicative increase, multiplicative decrease, which could seem to make a lot of sense, you will freeze a given unfairness situation. If one source has 10% and the other has 90%, whenever you will move with those multiplicative, you will freeze this unfairness situation. This is why we use AIMD, additive increase, multiplicative decrease, in this setting. And this is what congestion control in the internet is based on, at least partly. Because and this is the main part that was in DECnet. Then when it was applied to TCP, there were a number of other problems that were uncovered. And this is DECnet was network done in the mid-80s, 70s already. And everything was very slow, everything was very small, and it worked well. So the problem was really to avoid the congestion collapse. Then a bit later, 10 years later, we started having a network a bit faster, and then we started having some inefficiencies if we just use AIMD. So the theory that we've done is a long-term theory. If you have sources that take a long time to transfer something, then our theory covers what we do. Then when we move with technology, long becomes less long. The higher the bit rate, the less long it takes for you to transfer over a given link. So the transients start to matter a bit. In order to address this, we add to AIMD another mechanism that's developed ad hoc, doesn't have a theory behind it, that is called slow start. So slow start is addressing the problem that is given here. Here you saw on the x-axis time, on the y-axis you saw the rates of 3 sources that uses AIMD, and you assume that those 2 of the sources, the green and the blue, were there before. So it's a zoom on what we have seen previously. The third sources started later. Then we see that this guy, the red guy, has to compete with 2 other sources that fill the pipes, so it will increase, then very quickly it will cause congestion. It will divide its rate by 2 and will continue increasing. Then it will see congestion, it will divide its rate by 2, and after some time, everything will be more or less, in this ideal case, synchronized. In reality, they're not synchronized, but they oscillate around a value which is the same for all. Here I'm plotting phase diagram, so-called phase diagram, source 1 versus source 3. So we see the source 1 started at 4, source 3 at 0, and we see that the number of oscillations it takes to reach the line of fairness here is very long. So it takes a large number of steps for source 3 to reach the same rate as others. Is that a problem? Is that not a problem? As I said, it's not a problem if you expect the flows to be very, very long, but if at time 400 the red source is finished, then this fairness is not good enough. In other words, the transients of additive increase, multiplicative decrease may be a bit too long. How is that fixed? This is fixed by adding another algorithm, which is called slow start. Slow start, be careful with the terminology. Slow start is, the way I present it, is a fast start. It is slow compared to a source that would not be congestion controlled. Before congestion control existed, so the first version of TCP, there was no congestion control. So the only thing that controlled the source was the window advertisement. A TCP source received a window of 10,000 bytes. Bing, it sends 10,000 bytes instantly. This was considered a hot start. If you use this algorithm, you will not send immediately the 10,000 bytes, you will gradually increase. But compared to AIMD, it's a very fast increase because it is a multiplicative increase. So the idea is to mitigate the things we've seen before. We need an adaptive algorithm. We need to test the water before sending. But if you come the last and in front of a crowd that is sharing a bottleneck link, you may perhaps want to very quickly test the water to see what is the state of what others are obtaining. So the idea is that you start, so this is showing on the x-axis the rate of a source that applies slow start. You start at the minimum possible rate. For TCP is 1 MSS per round trip time, so a window of 1 MSS. And then you increase multiplicatively. So you apply multiplicative increase. That means as long as there is no negative feedback, no congestion feedback, you continue increasing. And the idea is that in most cases when you start, if the network is not severely underdimensioned, you should be able to send a number to do that, and there is some available capacity for you that you're able to test. Now, when you reach congestion, that means you have reached the limit, the capacity of the bottleneck link in this naive model where there's a single bottleneck link. Now, what should you do there? Well, here it means that you are reaching the capacity, and then to avoid the inefficiencies, congestion collapse and everything, then you don't want to continue increasing exponentially. Therefore, we use another variable which is called the target rate. So there is a physical rate at which you send, and the target rate. In TCP, this is called the congestion, it corresponds to the congestion window and the slow start threshold. We'll talk more about that a bit later. This target rate is the rate that you're trying to get if you would apply AIMD. So here, when you reach a loss, then you say, my target rate, how much I should be sending, just after the loss, I divide it by 2 by taking as a basis the rate I had reached here. So in some sense, I'm saying when I reach that status, I have tested what is more or less the rate that others have, and I apply multiplicative decrease to me. So I have, so the initial value of the target rate is the maximum rate that you can send, and which of course you will not reach because you move on exponentially, you increase exponentially. When you reach congestion here, the value just after the congestion of your target rate is half the value that you had reached here. So half of that value is what gets here. And then when you have a second congestion indication, you redo the same, you test, you want to be careful, so you start again from 0 or from the minimum, and you increase until the same thing happens or until you reach this half rate here. If you reach this half rate, that means this guess was correct. This was indeed the rate that you would have reached in the stationary regime after a long term. And if your guess is correct, then you can stay. And here you exit slow start. Then you go into the normal additive increase, multiplicative decrease mode. So you have a special treatment for the transient phase, which has a beginning, which is when you start a connection, and an end, which is when you reach your target rate here, which gives this algorithm that I led to you to discover. But let's look at what happens to these sources here. So here, the third source, of course, it's not very visible what has happened here. If we have a slow start here, in the previous case, we saw the source took a long time to reach at the same level as the others. Here we see that at the beginning, it will increase, and it will go somewhere which is between the blue and the green. That will cause a congestion, and then it will receive a feedback. This is the first feedback here. So the first source 3 increases, and then it sees it has, which is probably somewhere here. Then it halves, the rate that it gets here becomes the half of the rate becomes the target rate. It will continue increasing. And then, because this increase is exponential, is very fast, it gets into the region where it is competing fairly with the others. So if we compare this scenario with the absence of slow start, which was the one we saw before, we see that, as expected, this allows the red to go much more rapidly to the same share as the others. This is slow start. It's less beautiful to teach. There is no nice theory of why we do it like this. It's a pragmatic approach that says, we have a theory that says for long-lived flow, AIMD is good and provides fairness, as we'll see later. In practice, however, it may take a long time in the transient phase, and we solve this transient phase by this ad hoc thing, which is called slow start. In summary, congestion control, as we have seen, is necessary to avoid inefficiencies, and more than inefficiencies, collapses. We need a congestion control mechanism, and it should agree on some form of fairness. And in the internet, the means to implement some rate allocation are based on AIMD primarily, and slow start as an additional mechanism. Now let us see how this is done in the internet now practically.